Hi everyone. We're going to continue our discussion on functions, and the next thing we're going to talk about are operations on functions. Just like numbers, functions can be added, subtracted, multiplied, and divide. And there's one additional operation that functions can have, but we're going to talk about that in another video. So, we're going to do some examples of these operations with functions, but one of the things we also have to consider with functions that we don't have to consider with real numbers are their domains. And domains are, so if you know how to define a domain of a regular function, finding domains of these added, subtracted, multiplied, divide functions are very easy. For adding and subtracting, you follow this procedure. You just find the domain of f, find the domain of g, and then just find what values in the domains they have in common. And it sounds maybe complicated, especially for some of you who are nervous about domains, but as you see, if you just draw them in number lines, and we'll see that in an example, that it actually becomes very simple. You just, basically everywhere you shaded in both number lines is the domain of the function. Now, for division, the first three steps are the same, but we had this added fourth step here, whereas that once you find everything they have in common, then you have to delete any value of x that makes the denominator function g of x 0. So we'll see that in the examples as well. So let's move on to our first example. We're going to find the sum, the difference, and the product of these two functions. And notice that domain is all follow the same procedure, so all three of these functions are going to have the same domain. So let's start off with the plus. We have f plus g of x. Now this is just shorthand notation for f of x plus g of x. And so we just f of x, well, we look at what it is. It's just x plus 3. So we write that in. G of x, well, that's just this function here. So we write it in, plus the square root of 2x plus 3. And there's no simplification that can be done here, so we just leave it as that. Subtraction is very similar. Again, f minus g of x is just shorthand notation for f of x minus g of x. And this time we will have x squared plus 3, since f of x is this function, minus the square root of 2x plus 3, since g of x is equal to that function. Now the only thing you have to be aware with subtraction is if we had more than one term, you would have to distribute the negative. Now lastly, we want to look at fg of x, which is an abbreviation for f of x times g of x. Now this one we'll have to do a little simplification for, since f of x is x squared plus 3, and then g of x is the square root of 2x plus 3. And this is a perfectly fine form to leave it in, probably actually a little better than what I'm going to do, but you technically distribute the square root of 2x plus 3 to both terms here, and get x squared times the square root of 2x plus 3 plus 3 times the square root of 2x plus 3. But this is really the kind of the nicer, more simpler form, so I would have probably left it in that, but technically you can multiply it out and get this instead. So the only thing left is to find the domains. So the first thing I said was to find a domain of f, so we usually abbreviate this with d with a subscript of f. And notice that this is a polynomial, so it's going to be all real numbers. And so on a number line, it's going to look like this. So we're going to have the number line, and we are just going to fill everything in. So, well, let me draw on 0 for a relative spot. And then we color the number line everywhere it's defined, so it's defined everywhere. So for so now we want to find domain of G. So let's give myself a little more room. So the domain of G. Well, how do you find domains of radicals? Well, remember, we're going to take this part under the radical and set it greater than or equal to 0 and solve for x. So we're going to have 2x greater than or equal to 3 and x is greater than or equal to 3 halves. And so our domain is going to be 3 halves, comma, affinity, and since we have the equal sign, we get a closed bracket here. And so on the number line, here's 0, but here's 3 halves, and we're going to include 3 halves and fill in every x value that's greater than 3 halves. So now we need to find the actual domain of all these functions. So the way we usually write it, my other example creeped in on us. So let's actually pull that off and go this way. So step 3 is we want to find the domain of f plus g, which turns out to be the same domain as f minus g, which turns out to be the same domain as f times g. So we have from here, so I'm just going to copy this and move it over here. I'm going to take this. Oops, took too much. So let's try again. I'll take this, copy it, move it on over here. Let's see, paste, move it up so the 0 lines up. And this was 0 to begin with. And so we want to ask, where did we color in red in common? And notice that we only colored in red in common from 3 halves and everything greater than 3 halves. So our domain is going to be everything in common in both, so that would be 3 halves, comma, affinity. And so our domain as a number line is just identical to the domain for G in this case, since G was the more restrictive domain here. Now, just be aware that the domains of these operations are not always the domain of one function or another. As we'll see in the next example, we can actually get something that is is different than either one of the domains of the constituent functions. So let's do our last example, which is about the quotient, and then we do the quotient separately because its domain is found separately. So first thing we want to do is figure out algebraically what f comma or f over g is. So f over g of x is an abbreviation for f of x all over g of x. And then we just plug in what f of x and g of x are. So in the numerator we'll have x squared plus 1 all over, and unfortunately with this problem, which was intentional in my design, but unfortunate when you ever encounter it, is that we have a fraction within a fraction. But what we're going to have to do here is the normal flip and multiply technique. So we're going to have from the numerator x squared plus 1, and remember that if you don't have a fraction, you can always turn it into 1 by thinking it over as 1. Then we're going to take the denominator and flip it over, and we're going to have x over x plus 1. And when we simplify that, we get x squared plus 1 times x all over x plus 1. And then we can simplify that to x cubed plus x all over x plus 1. So this is what algebraically the quotient simplifies to. So we want to find the domain next. And this is where you have to be careful a little bit here. So the first three steps are the same. The domain of f. Well, the domain of a polynomial is always the real line. So that's just negative affinity to affinity. So if we draw the real number line, we get everything. So step 2 is to find the domain of G. Well, the domain of G is anything that makes the denominator not equal to 0, so set the denominator equal to 0. And I chose a very simple denominator here, so we just get x equals 0. And so this is the only value we have to exclude, so the domain is going to be negative affinity to 0 union 0 to affinity. If you forget what the union symbol means, it's just a symbol in math that means or. So it's either negative affinity to 0 or 0 to affinity are the values of x that we can throw in. And so when we draw our number line, we have 0 here, but when we fill everything in, but when we get to 0, we have to put in this open circle to represent that we took out that point. And then step 3, again, is the same as before. We combine, so we take this graph. Let's do what I did before and go this way. So step 3. So we take this graph, copy it, move it over here, move it a little bit into a better position, and that was 0 here. Now let's do the same with this graph. We'll copy it, maybe, there we go. Copy it, paste it over here. Wow, I pasted it way over there, so let's move it back. Making sure the zeros get roughly lined up. And so we want everything that's in common. Well, let's make this a little bit more obvious that that was circled there. And so notice that at 0, we left out that point. So our domain here are not our domain. So, but for step 3, what we're going to get in common, so let me write in common, is that we are going to get, so here's 0 on the number line, so we're going to get everything on the number line except the point 0. Alright, but remember there was a step 4, so let me remind you what step 4 is. And step 4 is we need to delete any value of x that makes g of x equal to 0. Because if it makes g of x equal to 0, let's look here, then this denominator is equal to 0, and that means that it's undefined because we can't divide by 0. So we need to figure out what values of x make g of x 0. So let's look at our g of x again and remind ourselves what it is. And g of x here, in this case, is x plus 1 over x. So we need to figure out what makes this undefined. So what makes g of x equal to 0? So let's do a step 4 here. And so we get that g of x is equal to x plus 1 over x, and we want to solve x plus 1 over x equals 0. So notice or recall that a fraction is 0 equal to 0 if the numerator equals to 0. This is a fact you should have learned in a previous course, but in case you've forgotten or somehow missed that detail, that is always true. So the only thing we have to solve is actually, the only thing we have to do is look at x plus 1 equals 0. So if we solve that, we get x equals -1, and this value we're going to have to exclude from this number line. So our domain then for f over g is going to be everything from negative infinity to -1, union -1 to 0, union 0 to infinity. And for your visual people, we'll draw this on the number line. So here's 0, here's -1, and so we'll fill in everything until we get to -1. We'll exclude -1, keep filling in. At 0, we'll exclude 0, and then we keep filling in. So every point except for this one and this one will be defined for our function. These are the only 2 points that would be undefined, and that makes sense when you actually look at the composition, or not the composition, the division here, because we can't have 0 because it makes g of x 0, but we also can't have -1 because look at what -1 does here. It makes this denominator equal to 0 as well. But you have to be careful with division because it's not always obvious when you look at the final form here that -1 should have been thrown out. It's just obvious because it's a simple function here. So this is definitely a way you find domains, this 4-step procedure. You find the domain of f, you find the domain of g, you find what they have in common, and then you see what makes g equal to 0, and throw it out. Alright, that will be all for this video. So in the next video, we'll talk about the new operation called composition. See you then.